Blow a soap bubble. Go ahead. Picture it. You dip that little wand into the dish soap. You blow, and out comes this perfect, shimmering sphere floating through the air. Beautiful thing. Everybody's done it. Kids love it. Adults pretend they don't love it, but they do. Now let me ask you something that sounds so simple you might laugh. Why is it round? I don't mean sort of round. I mean perfectly, mathematically, flawlessly round. Not an oval, not a lumpy blob. A sphere. Every single time. You never blow a soap bubble and get a cube. You never get a pyramid. You get a sphere. Why? Well, you might say it's surface tension. Fine. Good answer. But that's a name, not an explanation. Saying surface tension is like saying a ball rolls downhill because of gravity. Sure, but what's actually happening? What is the soap doing? Molecule by molecule, and why does it end up as a sphere every single time? As if it attended a geometry lecture before you blew it out of the wand. Here's what's happening. The soap film is made of water sandwiched between two layers of soap molecules. Those soap molecules are amphiphilic, meaning one end loves water and the other end hates it. They arrange themselves with their water-loving heads pointing inward toward the water layer and their water-hating tails sticking outward into the air. This arrangement creates a stable film, but that film has energy, surface energy. And every molecule in that film is pulling on its neighbors, trying to contract, trying to shrink the surface down. The soap lowers the surface tension compared to pure water, which is why you can make a bubble at all. Pure water has too much surface tension to form a stable film. But the film still wants to be as small as possible. It's pulling inward from every direction, equally at every point. And the shape that encloses a given volume of air with the least possible surface area is mathematically a sphere. The ancient Greeks suspected this. It took until 1884 for the German mathematician Hermann Schwarz to prove it rigorously. But the soap bubble doesn't care about the proof. It just does it. Instantly, every time. No computation, no hesitation. It inflates, it wobbles for a moment, and then it settles into a perfect sphere, as if it had known all along where it was headed. All right, so that's cute. A bubble is round. Big deal. You already knew that. But now let me change the game a little. Instead of blowing a free-floating bubble, I'm going to take a piece of wire and bend it into a shape. Let's start easy. Bend the wire into a circle. Dip it in the soap solution. Pull it out. What do you get? A flat disk of soap film stretched across the circle. The flattest, smoothest surface you could imagine. And it makes sense, right? A flat disk has less area than any other surface you could stretch across a circular boundary. It's the minimal surface. The soap found it. Now bend the wire into something more complicated. Make a helix like a slinky with a straw connecting the ends. Dip it in. Pull it out. And what you get is part of a surface called a helicoid, this beautiful twisting ribbon-like thing. Or bend the wire into a square frame. You don't get a flat square. You get a surface that dips slightly inward, curving like a saddle, because that saddle shape actually has less area than a flat square would. The soap found the better answer. Now make the wire really weird. Twist it into some irregular asymmetric three-dimensional tangle. Dip it in. Pull it out. And the soap film stretches itself into this gorgeous flowing surface that hugs the wire at every point. It curves and dips and sweeps in ways that look almost artistic, like a sculpture. But it's not art. It's physics. That film has found in a fraction of a second the surface of minimum area that spans that wire boundary. This is a famous problem. It's called Plateau's problem, named after a Belgian physicist named Joseph Plateau, who devoted his life to studying these films in the 1830s and 40s. And Plateau's story is itself remarkable. He'd permanently damaged his eyes by staring at the sun for 25 seconds during an optics experiment. Think about that. 25 seconds of staring at the sun in the name of science. By 1843, he was completely blind. But he kept working. He kept experimenting. He had his family and his colleagues describe to him what the soap films were doing, and he ran his fingers along wire frames to understand the shapes. And what he discovered was extraordinary. He found that soap films don't just make pretty shapes. They follow rules, strict, precise geometric rules that never get broken. Not sometimes, not usually, always. Here's the first one. When soap films come together, they don't just crash into each other at random angles. 3 films always meet along a line, an edge, and they meet at exactly 120 degrees. Not 119, not 121, 120 degrees. Always. Plateau called these edges, where 3 films meet plateau borders, and the angle is always the same, no matter how complicated the frame, no matter how tangled the wire, no matter how many films are involved. 3 at 120. And here's the second rule. When those edges, those lines where 3 films meet, come together at a point, exactly 4 of them meet. And they do so at an angle of about 109.47 degrees. That's the tetrahedral angle. The angle you'd get if you put a dot in the exact center of a tetrahedron and drew lines out to the 4 corners. 4 edges meeting at one point at tetrahedral angles. Always. No other configurations are stable. This is the remarkable part. Let me show you what I mean. Take a wire frame in the shape of a cube. 6 faces, 12 edges, 8 corners. Dip it in soap. Pull it out. You might expect 6 flat films, 1 for each face of the cube, meeting at right angles along the edges. That's the symmetrical, obvious configuration. But that's not what you get. What you get instead is this intricate, sculpted shape with 13 distinct film surfaces. The films curve inward. They meet in groups of 3 along edges at 120 degrees. And near the center of the cube, there's a small, slightly warped square where the plateau borders converge. It looks nothing like a cube on the inside. It looks like architecture from another world. If you somehow manage to force 4 films to meet along a line at 90-degree angles, the way the walls of a room meet at a corner, the configuration would not hold. It would snap instantaneously. It would rearrange itself into 2 junctions of 3 films, each junction at 120 degrees. You can watch this happen in real time if you're careful. Build the unstable arrangement, and before you can even pull your fingers away, it pops into the stable one. The 4-way junction at 90 degrees has more total surface area, more energy, than the pair of 3-way junctions at 120 degrees. And the film finds the cheaper arrangement faster than your nervous system can register what happened. Why 120? It's not that nature has a preference for pretty numbers. It's that 120 degrees is where the forces balance. Think about it physically. Each film is under surface tension, pulling the junction toward itself, trying to shrink. When 3 films meet, you've got 3 pulls acting on the junction line. The only arrangement where all 3 pulls exactly cancel out, where the junction doesn't get yanked toward any one film over the others, is when the 3 films are equally spaced at 120 degrees. Each pull gets opposed equally by the other 2. Perfect balance. It's the same reason that if 3 people are pulling equally hard on ropes tied to a single ring, the ring will stay put only if the ropes are aimed 120 degrees apart. 2 people pulling in nearly the same direction would overpower the third. Any arrangement other than equal spacing means unbalanced force, which means the junction slides, which means the configuration isn't in equilibrium. And the tetrahedral angle at corners, 109.47 degrees, is the same idea in 3 dimensions. 4 equal forces pulling outward from a single point balance out only if they point toward the 4 corners of a regular tetrahedron. That's the most symmetric arrangement of 4 directions in 3-dimensional space. So when 4 plateau borders meet at a point, the tetrahedral angle is the only stable option. Now this is already pretty remarkable. A thin film of soapy water, something a child makes in the backyard on a Saturday afternoon, is solving a geometry problem that stumped mathematicians for over a century. Plateau described these rules from his experiments in the mid-1800s. But proving that these rules followed necessarily from the mathematics of minimal surfaces, that they were the only possible stable configurations, that took until 1976, when a mathematician named Jean Taylor nailed it down using a branch of abstract mathematics called geometric measure theory. More than 100 years of effort by serious mathematicians. And the soap film had the answer the whole time, just sitting there on the wireframe waiting for someone to notice. But all right, I can hear you thinking. Fine, the soap film is clever with surfaces and angles. So what? It's just doing what physics tells it to do. Water flows downhill too. Nothing really surprising here. So let me add another layer. Let me give you a puzzle. Imagine you've got 3 towns arranged in a triangle. Let's call them Town A, Town B, and Town C. You need to build roads connecting all 3 towns so that you can drive from any one to any other. And you want to use the least total road possible. You're on a budget. Every mile of road costs money, and you want to minimize the total. Most people's first instinct is simple. Connect each town to the other 2. Draw the triangle. 3 roads along the 3 sides. Done. But that uses too much road because you've got redundant connections. You don't need all 3 sides. Okay, so what if you just pick 2 of the 3 sides? Say the 2 shortest ones. That guarantees every town can reach every other town by traveling along at most 2 roads. And the total road is shorter, better. But there's an even better solution. One most people don't think of. Instead of just connecting the towns directly to each other, you add a new point somewhere in the middle. A junction, an intersection, and from that junction you run 1 road to each of the 3 towns, 3 roads radiating out from a central hub. If you pick the right location for that hub, the total length of road you need can be shorter than any combination of the sides of the triangle. Where is the right location? This is a problem that goes all the way back to Pierre de Fermat, the great French mathematician who posed it around 1643. He didn't solve it himself. He sent it as a challenge to the Italian mathematician Evangelista Torricelli. And Torricelli, a brilliant man who also invented the barometer, figured it out. He constructed equilateral triangles on 2 sides of the original triangle, drew lines from the new vertices to the opposite corners, and found that those lines crossed at a single point. That point is the optimal junction, the one that minimizes the total distance to the 3 towns. And here's the key property of that point. If you stand at the Fermat point, as it's now called, and look toward Town A, then turn to look at Town B, the angle between those 2 directions is exactly 120 degrees. Turn from B to C, another 120 degrees. From C back to A, another 120 degrees. 3 roads, radiating from a single point, equally spaced at 120 degrees. There's an important caveat. This only works if all the angles of the triangle formed by the 3 towns are less than 120 degrees. If one angle is 120 degrees or more, the Fermat point lands right on the vertex of that large angle. There's no benefit to adding a junction point. You just connect the other 2 towns to the obtuse angle vertex directly. The soap film handles this case perfectly too. When you dip the 3 pins, and one of the triangle's angles exceeds 120 degrees, the film stretches directly from that pin to the other 2. No central junction, it just knows. 120 degrees. Where have we seen that number before? The soap film. When 3 soap films meet along a line, they meet at 120 degrees. It's the same number. And it's not a coincidence. You can actually solve Fermat's problem with soap. Take 2 parallel sheets of clear glass or plastic. Drill 3 pins through both sheets, perpendicular to the surface, positioned at the locations of your 3 towns. The pins bridge the gap between the 2 plates. Now dip the whole sandwich into soapy water. Pull it out. The soap film stretches between the pins, forming thin vertical walls. and those walls arrange themselves into exactly the minimum network connecting the 3 points. 3 walls meeting at a central junction at 120 degrees, the Fermat point. The soap found it. Instantly. No compass, no equilateral triangles, no construction lines, no Torricelli. It just settled into the configuration of least surface area, which, because the film is stretched between 2 parallel plates, is equivalent to the configuration of least total length. And there it is, shimmering between the pins. The answer to a problem posed by one of the greatest mathematicians who ever lived, solved by a bit of dishwater and air. If you've never seen this done, let me tell you what it looks like in person, because the experience is more striking than any description. You dip the frame. You pull it out. And at first, the film is messy. It's attached to everything, forming closed bubbles and extra surfaces between the plates. You blow gently on the excess film, or pop it with a dry finger. And then, as the extra surfaces are removed, the remaining film snaps into position. You can see it happen. 3 thin vertical walls, stretching from one plate to the other, meeting at a point in the middle. The junction is sharp, clean, perfect. The angles are so precise that if you measured them with a protractor, you'd get 120 degrees to within the accuracy of your instrument. There's something almost eerie about watching it. You know that behind this simple physical event is a mathematical theorem, a proof by Torricelli, centuries of geometric reasoning. And the soap just does it, without any of that machinery, without any knowledge. It does it the way a stone falls, not because it understands gravity, but because gravity acts on it. The soap film doesn't understand minimization. Minimization acts on it, and the result is the same answer that all that mathematics produced. Let that sink in for a moment, but I'm not done. I haven't even gotten to the hard part yet. 3 towns is nice. Torricelli handled 3 towns. You can even do it with pencil and paper if you're patient. But what about 4 towns? Or 5? Or 10? Or 100? This is the generalization, and it's called the Steiner tree problem. It's named after the Swiss mathematician Jacob Steiner, although the problem was actually first stated by a French mathematician named Joseph Gergonne in 1811. Gergonne put it beautifully: a number of cities are located at known places on a flat surface. Connect them by a system of canals whose total length is as small as possible. You're allowed to add as many junction points as you like. The challenge is to figure out where to put them and how to connect everything to get the shortest total network. For 3 points with no angle greater than 120 degrees, you get 1 junction, the Fermat point, and the solution is elegant. For 4 points arranged in a square, the optimal solution has 2 junction points, connected to each other and to the 4 corners, with every junction having 3 lines meeting at 120 degrees. The total network is about 4% shorter than the obvious X pattern. Doesn't sound like much, 4%. But if you're laying fiber optic cable across a continent or routing connections on a microchip, 4% of billions of dollars is a lot of money. For more points, you can get many junctions. But the same rule always holds. At every junction, exactly 3 lines meet, and they meet at 120 degrees. That's a theorem. It follows from the same forced balance argument I described for soap films. These extra junction points are called Steiner points, and the optimal network is called the Steiner minimal tree. Now here's where this story takes a turn that I think is genuinely shocking. The Steiner tree problem is what computer scientists call NP-hard. I won't bore you with the formal definition, but let me tell you what it means in practice. It means that as the number of cities grows, the time it takes the best-known computer algorithm to guarantee finding the optimal solution doesn't just grow gradually. It grows explosively, exponentially. For 4 or 5 cities, a computer handles it easily. For 10, it starts working hard. For 20, it's sweating. For 50, you're waiting hours or days. For 100, you might be waiting longer than the sun has been shining. the number of possible configurations, the number of different ways you could place the Steiner points and draw the connections, grows astronomically with the number of cities. For 3 cities, there's essentially one possible Steiner topology, one junction point with 3 connections. Simple. For 4 cities, there are a handful of topologies. For 10 cities, there are thousands. For 20, millions. For 50, the number exceeds the number of atoms in the observable universe. I'm not exaggerating. The combinatorial explosion is that severe. And each of those topologies, each possible arrangement of Steiner points and connections, has to be evaluated. For each one, you need to find the optimal positions of the Steiner points within that topology, which itself requires solving a set of equations. Then, you compare the total lengths of all the optimized topologies and pick the shortest. Nobody has found a shortcut that avoids this explosion. The Steiner tree problem was among the original 21 problems proved to be NP complete by Richard Karp in 1972. It sits in this infamous class of problems that computer scientists strongly suspect cannot be solved efficiently. Not with current computers, not with future computers, not with any computer based on classical logic, period, unless our entire understanding of computational complexity is wrong. And essentially every expert in the field believes our understanding is not wrong. To give you a sense of scale, the best exact algorithms for the Steiner tree problem can handle maybe 20 to 30 points before the computation time becomes impractical. Beyond that, researchers resort to approximation algorithms, heuristic methods, clever tricks that get you a good answer, maybe within 1% or 2% of optimal, but that can't guarantee they found the best one. Entire research careers have been spent trying to push that boundary a little further. Companies that design computer chips spend real money, millions of dollars, on approximation algorithms for Steiner trees, because every millimeter of wiring saved on a chip translates to less heat, less power consumption, faster performance, and the soap film does it in a fraction of a second. Take your 2 sheets of plastic, drill your pins, 4 of them, 5, 6, dip in the soap, pull it out. Watch. The film stretches, quivers for a moment, and settles. And there, between the pins, is a network of thin soap walls connecting them all. Junctions of 3 walls meeting at 120 degrees, just like Plateau described. A candidate solution to the Steiner tree problem, produced in less time than it takes you to clear your throat. Now, I need to be honest with you. The soap film doesn't always find the absolute best solution. This is important, and I don't want to oversell the point. Sometimes the film finds what mathematicians call a local minimum rather than the global minimum. It's like a ball rolling across a bumpy landscape. The ball will roll into a valley, but it might not be the deepest valley. It might just be the nearest one. The ball can't see over the hills to find the absolute lowest point. It goes downhill from wherever it starts, and it stops when it can't go any lower without going uphill first. The soap film is the same way. It relaxes from its initial configuration, it contracts and reshapes, and it settles into a configuration that's a local minimum of surface area. For small numbers of pins, this is very often the true global minimum. For larger numbers, you might dip and withdraw the frame several times and get different networks each time, some shorter than others. The global optimum might not appear on the first try, or the second. You might need luck. The computer scientist Scott Aronson has made a very persuasive argument that you should not expect any physical system, not soap films, not quantum computers, not anything, to systematically solve NP-hard problems efficiently. Because if a physical system could do that, it would essentially constitute a proof that the mathematical class P equals the class NP, and essentially nobody believes that's true. The universe, for all its cleverness, probably can't cheat the fundamental limits of computational complexity. But here's the thing that still amazes me. Even when the soap film doesn't find the absolute global optimum, it finds something very, very close. And it does it almost instantaneously. It's a remarkable approximation engine. We have computer algorithms that approximate the Steiner tree too, and they're good. But they require careful programming, significant processing time, and sophisticated mathematics. The soap film requires a dish of soapy water and a wireframe. And it gets a comparable answer in a heartbeat. The reason is that the soap is not doing what a computer does. A computer, even a very fast one, is fundamentally a sequential machine. It checks options. It evaluates candidates. It uses clever heuristics to prune the search space, skipping over options that are obviously bad. But it's still searching. It's still comparing. The soap film doesn't search. It doesn't compare. It doesn't evaluate alternatives. Every molecule in the film is simply responding to the forces acting on it from its immediate neighbors. Each molecule is being pulled by its neighbors on all sides, and it moves to the position where those pulls balance out. That's all it's doing. It's not thinking about the global problem. It has no awareness of the other pins, the other films, the total length of the network. Each molecule is solving its own tiny local problem. Where should I sit so the forces on me are balanced? And yet, when all those molecules do this simultaneously, the global result that emerges is a solution, or nearly a solution, to the optimization problem. Not because any single molecule solved the big problem, but because the big problem is, in a deep mathematical sense, the sum of all the little problems. The global minimum of surface area is the configuration where every local neighborhood is also at minimum energy. Local optimality implies global optimality for these kinds of problems, for a certain class of them at least. And the soap film finds local equilibrium everywhere, all at once, in parallel, with as many processors as it has molecules. Think about the sheer scale of that parallel computation. A soap film 1 centimeter across, stretched between a few pins, contains something on the order of a trillion molecules, each one responding to its neighbors, each one adjusting its position, all of them doing it at the same time. There's no central controller, no master program directing the process, no molecule that knows what the other molecules are doing on the far side of the film. It's completely decentralized, completely local, and it converges to a global solution in the time it takes for the mechanical vibrations in the film to damp out, a fraction of a second. Compare that to a digital computer solving the same problem. The computer has to represent the problem abstractly, in numbers. It has to store those numbers in memory. It has to perform operations on them, one at a time, or at best a few at a time in parallel. Even with 1 billion transistors working at gigahertz speeds, it's processing the problem piece by piece, step by step. The soap film is processing the entire problem simultaneously at every point in space, using the laws of physics as its operating system and the molecules as its hardware. It's an analog computer. The most massively parallel analog computer you've ever seen, and you can make one for the price of a bottle of dish soap. There's a deep lesson here about the difference between analog and digital computation. Digital computers are flexible. They can solve any problem you can describe in symbolic terms. But they pay a price for that flexibility. They have to break continuous reality into discrete symbols, process those symbols sequentially, and then interpret the result. Analog computers, like the soap film, are inflexible. They can only solve the particular physical problem that they embody. But within that narrow domain, they're devastatingly efficient, because they don't break the problem into pieces. They solve it whole, all at once, using the physics itself as the computation. This is the key insight, and I want to dwell on it, because it connects to something much bigger. Let me give you another physical example before I take the big step, because I want you to see the pattern. Hang a chain from 2 hooks, a real chain, heavy, with many links. Let it sag under its own weight. What shape does it make? You might think it's a parabola. It looks like one, but it's not. It's a catenary, a special curve described by a hyperbolic cosine function. And why does the chain form that particular shape? Because the catenary is the curve that minimizes the potential energy of the chain, given its length and the positions of the endpoints. The chain doesn't know calculus. It doesn't know what a hyperbolic cosine is. It just hangs there, each link pulling on the next, gravity pulling everything down, and the shape that emerges from all those forces in balance is the one that makes the total potential energy as small as possible. The chain and the soap film are doing the same thing. The chain minimizes gravitational potential energy. The soap film minimizes surface energy. Both are physical systems relaxing into the state of least energy. Both are solving variational problems without knowing what a variational problem is. Now let me take you on what might seem like a detour, but trust me, it's not. When you throw a ball through the air, it follows a curved path, a parabola. Why that particular curve? Why not a straight line? Why not a zigzag? You can answer this with Newton's laws. Write down the forces, gravity pulling down, solve the differential equation, out comes the parabola. Done. And that works perfectly. But there is another way to think about it. A way that, I would argue, is deeper, more fundamental. In the 1740s, a French mathematician named Pierre-Louis Moreau de Maupertuis proposed something bold. He said that nature always acts by the simplest means. He proposed that there's a quantity which he called action, and that the actual path any physical system takes is the one that minimizes this action. The idea was refined by Leonhard Euler and Joseph Louis Lagrange into a precise mathematical principle. The action is calculated by taking the difference between the kinetic energy and the potential energy at each moment in time, and then adding up, integrating, that difference over the entire duration of the motion. The actual path the ball follows is the one where this total action is smallest. Or, more precisely, the one where the action is stationary, meaning if you nudge the path slightly, the action doesn't change to first order. This is called the principle of least action. And when I first learned it as a student, it blew my mind, because it seems to imply that the ball knows where it's going before it gets there. It seems to imply that the ball surveys all possible paths, calculates the action for each one, and picks the cheapest one. That sounds crazy. A ball doesn't think. A ball doesn't plan ahead. And yet, the mathematics says the ball's path is the one that minimizes the action, as if it had considered all alternatives. The resolution, of course, is that the ball doesn't actually survey all paths. The principle of least action is mathematically equivalent to Newton's laws. If you start from Newton's equations and do some calculus, you can derive the least action principle. And if you start from the least action principle and do some calculus, you can derive Newton's equations. They're the same physics, described from two different vantage points. Newton's laws are local. At each instant, the ball responds to the forces acting on it right now. The least action principle is global. The ball's entire trajectory is the one that makes the action stationary. But here's why the least action viewpoint matters. It generalizes. Newton's laws work great for balls and planets. But when you get to electromagnetism, to general relativity, to quantum field theory, the force and acceleration approach becomes unwieldy. The principle of least action still works. All of modern fundamental physics, the Standard Model, Einstein's gravity, everything, can be derived from action principles. You write down the right action, you minimize it, and out come the equations that govern the universe. And the soap film is the same idea, made tangible, made visible. The soap film is minimizing its surface area, which is proportional to its surface energy. The equilibrium configuration is the one where the total energy is at a minimum, subject to the constraint that the film is attached to the pins. This is a variational problem. It's the same type of mathematics, the calculus of variations, that gives you the principle of least action, that gives you the shape of a hanging chain, the path of light through a lens, the geodesics on curved surfaces. The connection to light is particularly beautiful. In the 1660s, Fermat himself, the same Fermat who posed the three-town problem, proposed that light always travels the path that takes the least time. In empty space, this is a straight line, because the fastest path between 2 points in a uniform medium is a straight one. But when light passes from air into glass, it bends. It refracts. And the angle at which it bends is exactly the angle predicted by assuming it chose the path of least total travel time. Light moves slower in glass than in air. So it minimizes its time by spending as little distance as possible in the glass. It bends its path at the interface to achieve the fastest trip. Fermat's principle of least time. The principle of least action. Plateau's minimal surfaces. These are all the same underlying idea, wearing different costumes. Nature minimizes, or to be more precise, nature finds the stationary points of certain quantities, the configurations where small perturbations don't change the cost to first order. And from that single tendency, all the structure of the physical world flows. The 120-degree angle, the number that keeps appearing, is a consequence of this minimization. When three equal forces pull on a point, the only stable arrangement is the one where the forces are 120 degrees apart. That's why the Fermat point has 120-degree angles. That's why Plateau's borders meet at 120 degrees. That's why the Steiner tree has 120-degree junctions. It's the geometry of balanced tension, the geometry of economy, the geometry that arises when nature is being as frugal as it possibly can. Let me push this even one step further. Carl Friedrich Gauss, one of the greatest mathematicians of all time, was interested in the Steiner problem too. In a letter to the Danish-German astronomer Christian Schumacher in 1836, Gauss wrote about the problem of connecting four German cities, Harburg, Bremen, Hanover, and Braunschweig, by the shortest possible railway network. This was not an abstract exercise. Railways were being built across Europe. The money was real. And the mathematical question of optimal network design was a practical engineering challenge as well as a theoretical puzzle. Today, the Steiner tree problem shows up everywhere. In the design of integrated circuits, where you need to connect transistors on a microchip with the minimum total wiring. In telecommunications, where you want to minimize the fiber optic cable connecting network nodes. In pipeline routing, in road planning, in the design of heating systems. Anywhere you need to connect a set of points with the minimum total cost of connection, you're facing a version of the Steiner tree. And in every one of these applications, the soap film solution is sitting there, offering its hint. Not as a practical engineering tool, because for real-world problems you need precision and guarantees that a soap film can't provide, but as a proof of concept, as a demonstration that nature knows how to solve this kind of problem, even though our most powerful computers struggle with it. Let me give you one concrete example that really brings this home. Take 4 pins at the corners of a square, with the side length being 1 unit. What's the shortest network connecting all 4? The obvious guess is the X, 2 diagonals crossing at the center. Total length 2 times the square root of 2, about 2.83 units. But that's not optimal. The optimal Steiner tree for a square has 2 Steiner points, positioned on the vertical center line, each connected to the 2 nearest corners and to each other by a short horizontal segment. 3 lines meet at each Steiner point, all at 120 degrees. The total length of this network is 1 plus the square root of 3, about 2.73 units. About 4% shorter. Dip a frame with 4 pins at the corners of a square into soap. You will never get the X. Never. Because the X would require 4 films to meet at the center at 90 degrees, and that's one of the configurations that's unstable. Plateau's rules forbid it. The 4-way junction at 90 degrees has more energy than the alternative configuration with 2 3-way junctions at 120 degrees. The film snaps instantly into the Steiner tree. It finds the better answer, because it physically cannot remain in the worse one. This is so different from how a computer works that I think it deserves emphasis. A computer, when confronted with the 4-pin problem, might enumerate the possible network topologies, evaluate the total length of each, and pick the shortest. That's a search. The soap film doesn't search. It can't stay in the wrong configuration even if you try to force it, because the wrong configuration is unstable. It's like trying to balance a ball on top of a hill. You can put it there, but it won't stay. The slightest perturbation sends it rolling into the valley, and the valley is the answer. The soap film finds the answer not by looking for it, but by being unable to be anywhere else. There's something profoundly humbling about this. We build machines with billions of transistors, switching trillions of times per second, running sophisticated algorithms written by brilliant programmers. And for certain problems, a film of soapy water, thinner than a human hair, outperforms them all. Not because it's smarter, because it's not computing at all. It's just being physical. It's obeying the laws of physics, and the laws of physics naturally drive it toward minima. The mathematician Richard Courant, who taught at New York University, loved to demonstrate this. In his classic book, What is Mathematics?, written with Herbert Robbins and published in 1941, he described these soap film solutions beautifully. He apparently kept wireframes and a dish of soap solution in his office, and when visitors came by, mathematicians, physicists, anyone, he would show them. Dip the frame, pull it out, point to the network, and watch their faces. He considered it among the most elegant demonstrations in all of mathematics, not a demonstration of soap physics. A demonstration of the unity between mathematics and the physical world, not because the soap was doing anything clever, but because it revealed the deep unity between physics and optimization. The soap film doesn't solve a math problem and then do physics. It doesn't do physics and then incidentally solve a math problem. The physics and the mathematics are the same thing. The minimum surface and the balanced forces are two descriptions of the same reality. And this unity is not limited to soap films. It's everywhere. The shape of a hanging chain, the curve called a catenary, is the shape that minimizes the potential energy of the chain subject to its length. The path of a ray of light through a stack of glass layers is the path that minimizes total travel time. The orbit of a planet around a star is the trajectory that makes the action stationary. The shape of a cell membrane is influenced by surface energy minimization. The branching pattern of blood vessels in your body follows an optimization principle, minimizing the energy needed to pump blood while maximizing the coverage area. Honeycombs are hexagonal because hexagons are the most efficient way to tile a plane with cells of equal area using the least total wall material. That was conjectured for centuries and finally proved mathematically by Thomas Hales in 1999. But the bees didn't wait for the proof. They just made hexagons. The universe is, in its deepest nature, an optimizer. Not in the sense that it's deliberately trying to optimize. It has no mind. It has no goals. But the laws that govern it are laws of extremization. They're variational principles. And the solutions to those variational principles are the shapes and motions and configurations that we observe. Let me give you a few more examples, because I want you to feel how pervasive this is. A raindrop falls through the air. Why is it shaped the way it is? Small raindrops are nearly perfect spheres, minimizing surface area for their volume, just like a soap bubble. Larger raindrops flatten into oblate shapes because air resistance deforms them, and the equilibrium shape minimizes the total energy, which now includes both surface energy and the energy of deformation from the air drag. The raindrop is solving an optimization problem as it falls, a different problem than the soap bubble, but the same kind. Minimization of energy subject to constraints. A snowflake grows in a cloud. Each arm extends along directions dictated by the crystal lattice of ice, which itself is a minimum energy arrangement of water molecules. The hexagonal symmetry of snowflakes is a consequence of the fact that water molecules minimize their energy by arranging into hexagonal lattices. The specific branching pattern of each arm depends on the temperature and humidity the crystal encounters as it falls, but the underlying hexagonal geometry is universal. It's the geometry of minimal energy for the H2O molecule in its solid state. A river cuts across a landscape. The path it follows is not random. It follows the path of steepest descent, which means it's always moving in the direction that reduces its gravitational potential energy most rapidly. When it encounters an obstacle, it doesn't stop and reconsider. It just goes around, finding the path of least resistance, which is equivalent to the path that minimizes the total energy dissipated as the water flows from high ground to low ground. Rivers meander because straight channels on gentle slopes are actually unstable. Small perturbations grow, and the meandering pattern is a different kind of energy equilibrium, one that balances erosion on the outside of bends with deposition on the inside. Bubbles are spheres because spheres minimize area. Soap films meet at 120 degrees because that minimizes local energy. Light bends at interfaces because bending minimizes travel time. Particles follow trajectories that make the action stationary. Crystals form lattices that minimize bonding energy. Rivers follow paths that minimize gravitational potential. Everywhere you look, the same principle. Minimize. Extremize. Find the configuration where small changes don't help. And when you put pins in a soap film, you're giving nature a problem, connecting these points with minimal total material, and nature solves it, not by thinking, but by relaxing. By letting every molecule find its own local balance, by allowing the whole system to settle, simultaneously and in parallel, into the cheapest configuration it can find. This is what the soap film is really showing you. Not just a clever trick with pins and dishwater. It's showing you the deepest organizing principle of the physical world. The universe doesn't crunch through possibilities the way a computer does. It just relaxes into the answer. And that answer, or something breathtakingly close to it, emerges from the collective behavior of billions of molecules, each one knowing nothing about the global problem, each one simply responding to its neighbors. You know, we spend our lives building machines to solve problems. We write code. We construct algorithms. We design elaborate logical architectures. And they're wonderful, those machines. They've transformed civilization. But the deepest lesson of the soap bubble might be this. The universe was solving problems long before we came along. It was doing it for billions of years, in every raindrop that found its shape, every crystal that grew its lattice, every soap film that stretched across a wire frame. It doesn't need our algorithms. It just does what it does, follows those few elegant principles. And the answers appear. That, to me, is the most beautiful thing in physics. Not any particular equation, not any particular experiment, but the recognition that the world is built on principles of economy, that the laws of nature are, at their mathematical heart, statements about minimization, and that a soap bubble, a child's toy, a thing you can make in your kitchen for pennies, embodies those principles as completely and as elegantly as any equation ever written. So the next time you see a soap bubble drifting through the sunlight, casting those swirling rainbows, think about what's really happening inside that film. Think about the fact that its shape encodes a solution to a problem that took the finest mathematical minds centuries to even formulate. Think about the fact that the angle at which its surfaces meet is the same angle that minimizes road networks, the same angle that shows up in the design of efficient circuits, the same angle that results from the balance of equal forces. Think about the fact that the principle governing its shape, the principle of minimization, is the same principle that underlies every fundamental law of physics we've ever discovered. A thin film of soapy water. That's all it is. And inside it, the same principle that runs the entire universe. Here's what I want you to think about. The next time you face a problem that seems impossibly hard, a problem with too many options, too many variables, too many possibilities to search through, ask yourself, is there a way to stop searching and start minimizing? Is there a way to let the answer emerge, the way a soap film lets it emerge, instead of hunting for it step by step? Because that's what nature does. And nature has been at this game a lot longer than any of us. Tell me something. What other everyday thing have you encountered that might be secretly solving a hard problem, just by being what it is? I suspect there are more examples out there than any of us have noticed yet.